So, hello once more. Today we will continue the Fourier series expansion for the continuous wave signals. We have left at the periodic wave square example, and in previous lecture, remember we have defined synthesis and analysis equations. So today we will continue with more and more examples. Well, in the example, we are asked to find the Fourier series coefficients for the periodic square wave, which is defined over one period, as given that x of t is equal to 1 when t is absolute t is smaller than t1, and it is 0 otherwise within the period. So let me first start with plotting x of t. So this is just a periodic signal, and in the first, let's say around the origin, it is 1 in between minus t1 and t1, and it is 0 otherwise in the period. So it goes on like this from minus infinity to plus infinity. Also, there are negative parts that I have not plotted. So it's continuous as a periodic wave in this. So this is, let's say, 2t, and it goes on like this. This is, t plus t1. This is t minus t1. So this is periodic with t, and of course the period is here, as I mentioned, it is simply t. So how should I find the Fourier series coefficients? First one is a0. A0 is simple to calculate. So a0 is simply 1 over t, integral from minus t over 2 up to t over 2, x of t, e to power minus j. So for k, I will put 0, omega 0 t dt. So of course, the limits are from minus t over 2 to t over 2, but you know that within a period, only this interval is non-zero, so you can change this to minus t1 to t1. And the result is simple. I will just write it as 2t1 over capital T. So that's it. Well, what about ak in general? Ak is 1 over t, again, integral minus t over 2 up to t over 2, x of t, e to the power minus j k omega 0 t dt. So if you go and evaluate, it is 1 over t. I will change the limits to t1 minus t1 to t1. X of t is 1 whenever t is in the interval minus t1 to t1. So I will put here 1. So it is e to the power minus j k omega 0 t dt. Well, if you write, it is 1 over t minus 1 over j k omega 0 e to the power minus j k omega 0 t, evaluated from minus t1 up to t1, and it is 1 over t minus 1 over j k omega 0 e to the power minus j k omega 0 t1 minus 1 over j k omega 0 e to the power j k omega 0 t1. So that's it. So if you continue, it is 1 over t, 1 over j k omega 0 e to the power j k omega 0 t1 minus e to the power minus j k omega 0 t1. Well, these are straightforward, but I will solve for the first time. K omega 0 t and my e to the power j k omega 0 t1 minus e to the power minus j k omega 0 t1 over 2j. You know that the second term in square brackets is the sine, so it is simply 2 sine k omega 0 t1 over k omega 0 t. So these are the Fourier series coefficients in closed form for my periodic square wave, given as in this form. So the equation, formulations are simple. The derivation is straightforward, so you can, I'm sure you can do it easily by yourself. So, well, up to now, we have seen that if x of t equals summation k ak e to the power j k omega 0 t, then we have seen that it is periodic and the Fourier series coefficients are given by this integral equation. Well, but this observation does not prove that you can write any periodic signal in Fourier series form. Well, we have some, of course, rules for the existence of Fourier series representation. These are called as Dirichlet's conditions, and actually it requires your signal to have three properties. First one is that x of t should be finite energy, so it must be absolutely integrable over a period. So this is my first rule. The second rule tells you that x of t has finite number of maxima and minima within a period. And finally, x of t has a finite number of discontinuities within a period. So if you check those properties, actually the first one is not absolutely integrable. So these are extending to infinity. So when you integrate this over a period, you will see that you have infinite power. So this signal, or infinite energy. So the signal is not absolutely integrable. So you cannot write this signal in Fourier series expansion form. The second example has actually infinite number of minima and maxima. So the second signal has infinite number of minima and maxima, so it does not obey the Dirichlet's conditions. And on the other hand, the third signal finally has infinite number of discontinuities. So the third signal has infinite number of discontinuities. So it does not again satisfy Dirichlet's conditions. So almost all the signals that we will see actually will satisfy those properties. So, but be sure that you check whether it satisfies those three conditions. So, next thing that we will discuss is the properties of Fourier series. The first one is linearity. So, as you may expect, this linearity property is actually quite easy to prove. But first, what does it tell you? It tells you that if x of t and y of t are periodic with the same period and have Fourier series coefficients ak and bk respectively, then a linear combination of the signals a times xt plus b times yt has Fourier series coefficients a times ak plus b times bk. But before I start, actually, I will prove all of those properties by using the standard Fourier series expansion summation. So the synthesis relation I will use. So first write a times xt plus b times yt is equal to a times summation k ak e to the power j k omega 0 t plus b summation k bk e to the j k omega 0 t. So this is what I write, a times x of t plus b times y of t. Then this is simply, if you combine over a single summation term, a times ak plus b times bk e to the power jk omega 0 t. So this, of course, a times ak plus b times bk is the combined Fourier series coefficients for the linear combination signals, axt plus byt. So it is simple to obtain. Well, you know that summation is a linear operator, so you can put this inside. Again, since summation is a linear operator, you can combine the summation term in a single sigma sign. So that's it. Well, what if the signals have different periods, such as t0 and 2 times t0? Then, of course, you have, again, a periodic signal. And then what's the period? And how can you find the Fourier series coefficients of a times xt plus b times yt? So this is periodic with t0. This is periodic with 2t0. Then what happens if you sum them? So what's the period of the new signal? And how can you obtain the Fourier series coefficients? Well, this is for sure your homework. So please try this at home and be sure that you can find a solution for this. The next property is symmetry with real signals. If it tells you that if x of t is a real periodic signal, well, real means that x of t is equal to x conjugate of t, of course, then its Fourier series coefficients must satisfy ak is equal to a minus k conjugate. Well, how can I prove that? First, I will again start with writing x of t. It is simply summation k, ak e to the power j, k omega 0 t. And x conjugate of t, I know that, by the way, these are equal since x of t is a real signal. X conjugate of t is summation k. I will directly conjugate the first, this right-hand side. It is ak conjugate e to the power minus j, k omega 0 t. Well, I will simply make a change of variables, k equals minus k. Then in that case, it's equal to summation k, a minus k conjugate e to the power j, k omega 0 t. So while doing this, I will put minus k instead of k. So this minus k changed to k, and this plus k is changed to minus k. So when you compare those two, well, they are equal, you know that, since x of t is real. When you compare those two, actually a minus k conjugate is equal to ak. So this is equal to a minus k conjugate for a real signal. Well, easy to show, easy to prove. The third property gives us some alternative forms for Fourier series representation of real signals. Well, if x of t is real and periodic, of course, then you can derive two alternative forms for its Fourier series representation. So we will start with the first one. Well, actually, we will start with the general, and we will see that two representations are derived from the same idea. So let's start with writing x of t as usual, ak e to the power j, k omega 0 t. And I can write this as a0 plus the rest. So k from +1 to infinity. So I will simply separate this to, I have the term with a0, I have the terms with a plus minus, a1, a plus minus 2, a plus minus 3. So I will combine them into single summation in which the k runs from the positive values, and it is this ak e to the power j, k omega 0 t. So this is for the positive terms here, and for the negative terms, I will put the negative sign e to the power minus j, k omega 0 t. So here there is a simple trick. Well, I know that for real signals, I have this relation here. ak is equal to a minus k conjugate, or in other words, a minus k is equal to a k conjugate. So instead of this a minus k here, I will put a k conjugate. So if I continue, this is equal to a0 plus summation over k, ak e to the power j, k omega 0 t, plus ak e to the power j, k omega 0 t conjugate. So there is a trick here. I have omitted this minus sign and put here a conjugate over there. I know that a minus k is simply ak conjugate, so I put it here ak and put the conjugates outside. So here I have ak e to the power jk omega 0 t plus its conjugates. Well, I know that if you sum let's say a complex signal, complex number and its conjugate, you have 2 times the real. So it is equal to a0 plus summation k from 1 to infinity. This is the same. 2 times real ak e to the power j k omega 0 t. So if, let's say, my ak has such a form, ak times e to the power j phi k, so it's, I know that it's a conjugate number, so I can write it as in the polar form. Ak is the magnitude, e to the power phi k is the phase, so I can write it as ak times e to the power j phi k. Then in this case, x of t is simply a0 plus 2 times summation k from 1 to infinity real of ak e to the power j k omega 0 t plus phi k. Well, this is j k omega 0 t plus phi k. Well, of course, this is the exponential term multiplied with this term, so I sum the phases. So let's put here a parenthesis. Okay, I sum the phases, so j is out. So e to the power jk omega 0 t times e to the power j phi k is e to the power j times k omega 0 t plus phi k. So if you go further, you have as the first representation, this is equal to a0 plus 2 times summation k from 1 to infinity ak cosine k omega 0 t plus phi k. So this is my first representation, and the second representation I will write directly this 2 times summation k from 1 to infinity bk cosine k omega 0 t minus ck sine k omega 0 t. So this is my second representation, and I assumed that ak is in the form that bk plus jck. Well, in this case, you can write it as in this form. Well, if you have a real signal, then you can write it instead of a single summation. You can write it as the first a0 term and 2 times summation of cosines. So I note that I get rid of those e to the power something terms. So I can obtain my signal as sum of cosines in the first representation and with phase. And in the second one, I can write it as some cosine and sine terms. So by just using different notations for AK. So again, it is simple and easy to obtain. Well, the fourth property tells that if you have an even signal, note that even signals are satisfying this property, then you can write its Fourier series coefficients as this. It satisfies AK is equal to A minus K. So the proof is, as usual, starts with writing xt summation k ak e to the power j k omega 0 t, and I know that this is equal to x of minus t, and it is equal to summation k ak e to the power minus j k omega 0 t. So I have done nothing in that. This one I put it minus t instead of t. So now if you make a change of variables k to minus k, then in that case you have summation k from minus infinity to plus infinity a minus k e to the power j k omega 0 t. So if you compare this one and this one, you can say that ak is equal to a minus k for an even signal. Well, for the odd signal, you have nothing but the minus sign here, so this minus sign comes here. So you have the ak is equal to minus a minus k for an off signal. So the proof is similar. So I am giving you as a homework. The fifth property is about the periodic signals. Periodic signals are, important for our discussions. Here we have this notation over there. So we have the signal on the left-hand side, and we have the Fourier series coefficient on the right-hand side. Well, if you have this manipulated periodic signal, in that case, the Fourier series coefficients are somehow changing. Now, remember this manipulation discussions from the very beginning of our discussions. We have time shift, time reversal, differentiation, and other properties. So what is the effect of this manipulation on the, let's say, continuous time Fourier series coefficients? Well, we will start with time shift. So if you have x of t, which is, k ak e to power j k omega 0 t, then if you shift it and obtain x of t minus t0, then you have k ak e to power j k omega 0 t minus t0. I will put t minus t0 instead of t, so it's nothing. So this is equal to, and you continue from there, it's equal to summation k ak e to power j k omega 0 t times e to power, so there's a times here, times e to power minus j k omega 0 t0. So it's equal to x of t minus t0 is simply summation k. I write it here, so it is ak e to power minus j k omega 0 t0 e to power j k omega 0 t. So the new Fourier series coefficients are simply ak times e to power minus j k omega 0 t0. So this is my new Fourier series coefficients as given by this formula. So what about time reversal? If you have x of t with Fourier series coefficients ak, x of minus t has Fourier series coefficients a minus k. So how can I prove this? Now I will directly write x of t. It's equal to summation k ak e to power minus j k omega 0 t. And if I change k minus k, if I do k minus k substitution, then it is equal to summation k a minus k e to power j k omega 0 t. So this is my new Fourier series coefficients for x of minus t, so which proves this property over there. The last property that I will show you is the differentiation. If x of t has Fourier series coefficients ak, then the derivative dx by dt has Fourier series coefficients jk omega 0 times ak. So how to prove this? D by dt x of t is equal to d by dt summation k ak e to power j k omega 0 t. Then this is equal to, since my differentiation is a linear operator, I will simply change places. D by dt ak e to power j k omega 0 t. Of course, this ak does not depend on t. It is just a number, so I can put it out. And the derivative of this e to power j k omega 0 t is, j k omega 0 times itself. So if I continue, k j k omega 0 ak e to power j k omega 0 t. And this is the new Fourier series coefficients for derivative signal. Well, note that we have used that the property that differentiation is linear, so I can put it inside. AK does not depend on time, so I can put it outside the derivation. And if I do this, I have the new Fourier series coefficients as given by this formula. Well, we will continue with our LTI discussion. Well, please note that this LTI is important for our purposes. I can calculate the response of LTI systems easily for any inputs. So what if I combine those two? I have a signal which is periodic, and this periodic signal is input of an LTI system. If this is the case, then if your x of t periodic signal is at the inputs of an LTI system, you can calculate the outputs by this formula. Remember our HS or HJK omega 0. This is actually nothing but this here, e to the power minus st times h of t dt, and h of t being the impulse response of your LTI system. Well, actually, I will try to prove this. Remember from our discussions in the previous chapter, if you have h to the power st, which is input to an LTI system, by using direct LTI properties, linear and time invariance, we have shown that it's nothing but h of s times e to the power st, and this h of is nothing but your y0. So where h of s is this star here. So if h of s is given in this formula, then if e to the power st is at the input, at the output of this LTI system, you have h of s times e to the power st. So if I have s equals j k omega 0, well, note that here I have, instead of e to the power st, now I have e to the power e to the power jk omega 0 t. So in this case, of course, s is equal to jk omega 0. So if s is jk omega 0, then I have e to the power jk omega 0 t at the input, and at the output I have h of jk omega 0 times e to the power jk omega 0 t. Well, this is the case. So if you have e to the power jk omega 0 t instead of e to the power st at the input, at the output you have h of jk omega 0 times e to the power jk omega 0 t. So I have done nothing but in this relation, I have put s equals jk omega 0. Then, of course, since I have linear system, then y of t is simply summation k from minus infinity to plus infinity, ak times h of jk omega 0 e to the power jk omega 0 t. So remember, if you have a linear system, if you multiply this with, let's say, some ak, this is also multiplied with the same ak. So this relation, the last one, is exactly coming from the linearity. So we will see this with an example. So I have an LTI system with impulse response given by ht here. So what does this ht look like if you go and plot it? So if you assume t1 is larger than 0, then in this case, this is your ht, this is t1 over 2, this is minus t1 over 2, and this is 1, this is your ht, this is origin, and this is t. So ht is simple, it is 1 when t is from minus t1 over 2 up to t1 over 2. So what about x of t? X of t is your impulse response. Well, you know impulse response very well. Sorry, it is impulse train. You know impulse train very well. So if this impulse train is at the input to the system defined by this h of t, what is the output? So this is our case. So let's plot this x of t. So it is my impulse train. It goes on like this. So this is 0, this is t, this is 2t, this is minus t, this is minus 2t. It goes on like this from minus infinity to plus infinity. So what is, well, first I will write this x of t in the Fourier series expansion. So this is the beginning of everything, j, k, omega 0 t. Well, I know that ak is simply 1 over t, integral from minus t over 2 up to t over 2. Your x of t, which is delta t, e to the power minus j, k, omega 0 t, and dt. Well, this is by using this shifting property, you will put here, so this is non-zero whenever t is 0, so put here 0 instead of t, so you have simply 1 over t. So this is my, AK coefficients. By using the shifting property. Well, what about y of t then? Y of t is summation k from minus infinity to plus infinity. I'm not writing it. Ak h of j k omega 0 e to the power j k omega 0 t. Well, if I find h of j k omega 0, then I'm done. What about h of j k omega 0? I will use this formula exactly over there. It is simply integration from minus infinity plus infinity e to the power minus j k omega 0 t times my h of t. It is u of t plus t1 over 2 minus u of t minus t1 over 2, and I have here dt. So this is my h of j k omega 0, and if you go with the evaluation, it is from minus t1 over 2 up to t1 over 2. Well, this multiplication does nothing but limit the integral. So it is 1. So it is here. It is 1 in this period, in this interval. So it simply changed my integration limits and does nothing more. So e to the power minus j k omega 0 t dt. So if you go and evaluate this, I'm writing the result directly. It is 2 times sine k omega 0 t1 over 2 over k omega 0. And of course, omega 0 is 2 pi over t. So h of j k omega 0 is simply 2 times sine k omega 0 t1 over 2 over k omega 0. So if I continue from here, it's nothing but summation k from minus infinity to plus infinity. I have ak, but ak is 1 over 2. So ak is here 1 over 2. This 1 over 2 will cancel this t here. So you have sine k omega 0 t1 over 2 over pi k. So you have this pi here. This 2 will cancel this 2 here. This k will here, and this pi will come here. So you can see this by yourself. It's power j k omega 0 t. So this is my yt that I have obtained in the end. So if I plot y of t, what is it? You convolve an impulse train with a signal. So it shifts your signal. So you know this by heart. So y of t, of course, there are infinitely many terms here. So there are infinitely many terms here. If you sum them, you will finally obtain this y of t that I will write easily, because I'm convolving an impulse train with a signal. So I have this periodic signal. This is t1 over 2 up to minus t1 over 2. This is t. this is 2t, this is minus t. So it goes on from minus infinity to plus infinity. So you have nothing but the shifted version of h of t. So you have infinitely many terms. Well, our next example tells you that asks you to find the Fourier series coefficients of the periodic square waveform, but you can write it by using the above property. Well, if you have a periodic square wave, just as in this form, let's say, I have this y of t. This is my periodic square wave. It is simply this. It is going to infinity, t over 2 here, t here. So it is 1, this is minus 1. So this is my periodic waveform. I can write it as x of t convolved with h of t. And let's say my x of t is the impulse train. So this is x of t. So this is, let's say, 0. This is t. This is minus t. And my h of t is simply the signal. So this is t. This is minus 1. This is plus 1. So if you convolve this h of t with the impulse train, you will for sure obtain this y of t. Well, by using the above property, if you can calculate h of jk omega 0, then you can easily find the Fourier series coefficients for the periodic square waveform. Well, of course, you can do this by using the direct analysis equation. So you can integrate to find ak over a period, as we have done here for x of t. You can do this for y of t as you wish, but otherwise you can say that y of t is obtained by convolving x of t and h of t and use this formula over the top. So you can find h of jk omega 0 and easily find y of t. So this is what we will do in this case. So x of t is simple. It is an impulse train. It is k ak e to the power jk omega 0 t. Since it's an impulse train, ak is nothing but 1 over t. And I can obtain h of jk omega 0. It is from minus infinity to plus infinity, e to the power minus jk omega 0 t, h of t dt. And it is simply integral from 0 to t over 2. So if you go here, it is 1 from 0 to t over 2. So from 0 to t over 2 here. And it is minus 1 from t over 2 up to t. So h of jk omega 0 is simply integral from 0 to t over 2. Let's say 1 here for h of t. E to the power minus jk omega 0 t dt, plus from t over 2 up to t, it is minus 1 e to the power minus j k omega 0 t dt. Now you can easily calculate h of jk omega 0, then you can find your y of t as summation k ak h of jk omega 0 e to the power j k omega 0 t. So, and this ak times h jk omega 0 is, let's call this bk, and this is the Fourier series coefficients of your y of t. So the rest is, of course, your homework. You can obtain this h jk omega 0 and find bk easily. So we have more other properties, and please review this table and be sure that you can derive them, you can understand them. If there are some problems, please find me for this case. So This is for all for today. Next week we will be discussing continuous time Fourier transform. So let me